A tree is a more general data structure than a list because tree nodes can have at most one parent, but they can have any number of children. Because binary trees are the most useful, our discussion will focus on them. So let's consider how a binary tree differs from more general trees by stating its definition. A binary tree is a data structure consisting of a collection of nodes in which each node has 0, 1, or 2 children. So it differs from a more general tree in that every node can have at most 2 children. Binary trees can be categorized in a variety of different ways, but let's consider several special types of trees. A full binary tree is one in which all the levels are completely filled. One important feature of such trees is that there's a simple formula that expresses the relationship between the number of nodes in a full tree and its height. A complete binary tree is one in which all the levels, except possibly the lowest one, are completely filled, which is filled from the left. Complete binary trees will become important when we discuss heaps. Unfortunately, this terminology is not universal. You may encounter books which use these terms differently. A proper binary tree is one in which all nodes, other than the leaves, have 2 children. One important type of proper binary tree is an arithmetic expression tree that we will be discussing shortly. There are a number of other terms that are also important. Because every node can only have one parent, parent uniquely defines that node. But because there can be 2 children, they are distinguished by left and right child. Siblings are nodes with the same parent. Other nodes can also be classified. The one node that has no parent is the root node. Nodes that have no children are leaf nodes. Later we will see some other node classifications that are used most often in conjunction with proper binary trees. There are 2 other important characteristics of binary trees that are important. The first is the level of a tree, which is the distance from the root. We say that the root is at level 0. The other term is the height of a tree, which is defined as the maximum level of the tree. Another way to describe it is to say that it is the number of branches along the longest branch. Sometimes the height is defined as the number of nodes along the longest branch. The one advantage of this definition is that an empty tree will have a height of 0 rather than -1. To understand the structure of a binary tree, what we really need to understand is how each of its nodes are defined. In our binary tree class, we have used an approach similar to what we did with linked lists, which is to make the node class a nested class. Again, because there is no need for it to be an inner class, we declare it as static. Here is a depiction of a binary tree. It emphasizes the 3 components of each node: the reference to the left child, the reference to the data element, and the reference to the right child.